Can you guys see my screen?
Yes, sir.
Okay, yeah, good. So the years of air safety officer examination. So in aeronautical stream, though they mention it as an aeronautical stream, the propulsion part of this exam consists basically of aircraft propulsion and some turbo machinery basic ideas and few questions from the rocket propulsion. Rocket propulsion is not exactly there in the syllabus, but still they can ask few questions that is fundamental to a propulsion part. Okay. So now if I see the number of questions which is being asked, so I can see around 5 to 6 questions. The marks I am not exactly sure how many marks individual question carry, but there are
Sir,
around
18
5 to
marks.
6, 18 marks
Uh,
total.
oh, yes, sir. Total, sir. One question carry 3 marks.
Oh, okay. It is a constant, like every question is a 3-mark question, like ISRO
Yes, sir.
exam.
Yes, sir.
Okay, okay. Yes, yes, yeah. So then it makes your life easy. There are a few direct questions you can directly answer. So what I can see from this examination, from my point of view, is like they are not as hard as gate questions. They don't ask you a lot of theoretically intriguing questions. Rather, they ask more of memory based questions or a direct formula substitution kind of questions. That's what I can see from these questions. Anyhow, we can solve a few of the questions. So the first question I'm taking here is, there are 3 engines operate between a reservoir separated in temperature by 300 Kelvin. The reservoir temperatures are as follows. So the engine A has TH 1000 Kelvin, TC 700 Kelvin. Similarly, engine B has TH 800 Kelvin, TC 500 Kelvin. So engine C has 600 Kelvin and 300 Kelvin. So what you can see here is all the engines have a temperature difference of 300 Kelvin, right? That's what they mentioned. So now they are asking you to rank the engines in order of their theoretically possible efficiency, maximum efficiency, from highest to the lowest. So I can give you a 1 minute time. Can you quickly answer this?
Yes, sir. Like efficiency, sir, defined by output upon input. So output is total work divided by total heat input. So I think we can solve like output will be Q2 minus Q1 upon Q1, and then we can use the formula mcpdt, and from there I think we'll arrive at the formula, final formula minus T2 by T1, and
Okay.
so, and there, sir, I think we can found the efficiency. So if we go by this, if the TH is high, then the efficiency will be lower. So with sir, this I think explanation, it will be CBA. That's my answer, sir.
Okay. Okay. So here, whenever you see these kind of questions, right? So you don't have like enough data to approach from a basics. So what you have said, like if you are going to say the efficiency, the definition of efficiency is going to be the net work output to the heat input, right? That's the way how you define the efficiency. But you really don't have enough information. All you have is, you have a reservoir which is kept at some high temperature. In between you have an engine, then you are delivering it to a sink, say at low temperature. Simple idea. So now they are asking, what is the efficiency of the engine, theoretically possible efficiency of this engine. So if you have studied your Carnot cycle, so you encountered this. The highest possible efficiency for any heat engine is defined as the Carnot efficiency, that is 1 minus Tc by Th, right? If it is kept at Th and this is kept at Tc, this is the highest possible efficiency you can expect out of this given engine, right? So now, if you want to calculate the efficiency from the given data, the efficiency will be higher if this ratio Tc by Th is going to be smaller. So that is the part you have to look for. So if I take the engine A for this, if I calculate Tc by Th, what I am going to get? 700 divided by 1000. So that is going to be 7 divided by 10. So if I take the efficiency, that is going to be 1 minus 7 over 10. So or it is going to be 10 minus 7 divided by 10, that is 3 over 10. So going to be around 30%, right? Similarly, if I take for the engine B, what I get? Efficiency for engine B is 1 minus 500 divided by 800. So that is going to be 1 minus 5 over 8. So that is going to be 8 minus 5 divided by 8. So that is going to be 3 by 8. So now 3 by 10 and 3 by 8, which one is higher? The 3 by 8 will be higher, right? So similarly, eta C of engine C, you get 1 minus 3 over 6, that is 300 by 600. So that is going to be 50%. So when you compare this one, the engine C gets a higher efficiency than engine B than engine A. So the correct option would be from the highest to the lowest, you have C, B and A. So everybody clear?
No, sir.
Yes. What is your doubt here?
So you are used this formula, no, sir?
Hmm.
Formula, but your answer is coming 50%.
Oh,
Can you
sorry. Yeah.
explain, sir,
So
again?
okay. Yeah. So I'm getting your point actually. So let us see here. So how you define the Carnot efficiency? That is 1 minus the cycle minimum temperature to the cycle maximum temperature, or if you are using the reservoir like kept at engine and you are dumping into sink. So when you are keeping between these two, so then you can calculate the, this is where you are doing the Q in or Q out kind of thing. So now when you go on to calculate the work net to the Q in, that is nothing but efficiency of the Carnot cycle. So now if you do it for the Carnot cycle, you should end up with the efficiency as 1 minus Tc by Th. So this is a standard formula you have arrived, I think from your plus 11th or 12th classes, where whenever you introduce the idea of Carnot cycle, the efficiency of the cycle you have been introduced over there, and even in your engineering mechanics, again, or thermodynamics, again you studied this Carnot cycle. So this formula is very familiar to you. So now from the given options, I have engine A that has TH 1000 and TC 700. All they are mentioned is you have a engines they kept with the constant difference of 300 Kelvin, right? So if you take the B, you have Kelvin and 500. Again, the difference is 300 Kelvin. Similarly, you have engine C that is kept at 600 and 300. So the difference is again going to be 300 Kelvin. So if you use the Carnot cycle formula, you can get the efficiency as the first engine is 1 minus 700 by 1000. This gives you 30%. Similarly, for B, if you calculate, you get 1 over 5, 1 minus 500 over 800 gives you something around 31%. For C, you get 1 minus 300 by 800. So that gives you around 50%. So now, according to the given information, you get these as your efficiencies, right? This is clear, right, for you whoever asked the question?
Yes, clear.
Yeah. So, but there is a catch actually. Your question was right in the sense that even though theoretically possible maximum efficiency you can get out of the Carnot cycle, that cannot cross something around 40%. So, but from the given information, you are getting that. So that means like the information is not sufficient to comment on that, how you are getting the efficiency greater than that, right? You are getting my point, right? But from the given information, you can decide the engine C has a maximum efficiency than the engine B and then the engine A. That you can rank. But if I ask whether it is possible to have an engine with this difference or this efficiency, that is going to be a question that we need further data to confirm. Okay, shall we move to the next one?
So now we come to that question paper.
Okay.
Okay, sir, understood.
Right? Okay. Okay. This one is more of a practical question. So they are giving a condition that say you have a compressor and it is affected by the contamination. So now they are asking if the compressor is affected due to a contamination, then which of these statements are actually correct? So the statement 1 says the contamination of the compressor blades changes their aerodynamic shape. The statement 2 says reduces the airflow area, and statement 3 says more power and higher rotor speeds are required to achieve the desired compressor ratio or compressor pressure ratio. So the question is like, which of the above statements are correct? So I will go back to the question slide. What do you think?
Sir, first option, like contamination of the compressor, will it changes their aerodynamic shape? That is, I think, sir, logical. So, like if the contamination is uh, coming on the blade, it definitely will change the aerodynamic shape
Hmm.
and will affect. So we can go with the first option. And if
Hmm.
the first is true, and then we can also can think that the third will be also true. Like we need more power and higher rotor speed to achieve the compressor pressure ratio, because contamination has affected the aerodynamic shape. So it's not doing like this as it's supposed to work. So one
Okay.
and three, yes, sir, we can go. I was also thinking maybe second can be the answer, but from the option, this not all three are not true. So, sir, my perspective will be first and third.
Okay. Let us look at the options first. The first option says like 1, 2, and 3 are correct. So you have that option.
Yes,
The
sir.
D says 1 and 3 correct. C says 1 and 2. D says 2 and 3. So
Uh, then, sir, I think reduces the airflow area. I think, sir, we can go with the second also. Not sure, yours, but sir, I think it look like we can go with the second also. Yes,
okay,
sir. I think,
you
sir,
have,
we can go.
yeah, you have to be sure. Like you cannot have confusion whenever you are choosing the multiple options. Say, let us look this much more pictorially. So if I have the compressor, let us take any compressor. It doesn't matter whether it is centrifugal or axial now. Okay, let us try to stick with the uh, say axial compressor. Okay, I'm looking from the front view. So okay, so I have a compressor blades like this. Okay, so now if I just cut this section and weave it from the top, what I am going to see? I am going to see a set of blades arranged in this fashion. Right? This is one set of blade. This is next set of blade. Similarly, there will be a next set of blade like this. So usually looks like aerofoil. So I have a flow in this direction, say. So now what they're saying is like there is a contamination. That means there can be some external particles. They are coming on and sticking onto the surface of the profile. So if that happens, if I say like I had my aerofoil like this, it's a 2D view. So I had my aerofoil like this. Now there is a contamination. Some it can be a very irregular. It may not be very regular. Like aerofoil itself. So if there is a contamination on the aerofoil profile, obviously it is going to change the aerodynamic shape, right? You are not going to get the aerofoil. So the shape, now the flow has to see, is very different from what you have designed for. So the first option is directly correct because the contamination is going to change the shape of the aerofoil. Now, coming on to the second option, it says the effective area through which the mass is moving is decreasing. So now you see, if you look at this one, if it is an axial flow compressor, so what is your mass flow is going to be? Say this is your hub diameter, this is your tip diameter. This is the hub. So now, if I take the effective area through which the mass is going, that is going to be flux, which is going through the area. So density times the velocity, usually the axial component of velocity, that is normal to the area, and the area is pi dh square minus d tip square minus dh square over 4. So also you can write this one, because dt minus d hub is what? The dt minus d hub divided by 2 is nothing but the height of the blade. So I can write in this way, rho ca pi a square minus b square form, dt plus dh times dt minus dh divided by 2 divided by 2. So this one I can write as the mean diameter. This one I can write as the height of the blade. So this is the effective area through which a mass should go. And this is considering there are no blades present. The moment when you have a blades that is present, they are kind of an obstacles, right? You have blades present like this. So now the fluid can move only between the space between these blades, right? The fluid cannot go wherever there is a solid body. So the fluid can move only between the blades. We call this as annulus. So the fluid can move only within the annulus. So now, if you see, the contamination is there. Now your blades or this profile is becoming thicker, right? So now tell me whether that effective area is increasing or decreasing.
Decreasing, sir.
Hmm?
It's decreasing.
Decreasing, right? So whenever this profile is becoming thicker, the effective area is actually going to decrease. So now the mass which is coming in is not changing, but the area through which the mass is actually has to pass through, that is decreasing. So now what happens to the mass flow rate if that is the case? So I had mass flow rate that is equal to, say in the case 1, rho 1 CA1 area 1, and it should be equal to rho 2 CA2 A2. So this one without contamination, this one with contamination. So if the area is decreasing and say I have a same axial velocity at which a flow is coming, so there can be two ways. So either I can keep the density same, or I can keep the axial velocity to be same. So now say for the condition now, if the axial velocity is not changing, so the fluid is coming at a constant axial velocity, so now the density has to change, or it can be combination of both. So if I calculate the same mass flow rate at the end of the at the exit of the compressor, so there also you can have rho 2 CA2 some area. So let me call it as dash as CA2 dash and A2 dash. So now what happens if area is decreasing, then our assumption is such that axial flow machines should work with axial velocity by keeping axial velocity constant. But whenever there is a change in aerodynamic shape of the profile, then the axial velocity can change because of the uh, aerodynamic profile, whatever you wanted to design, that one you are actually changing now. So the performance is not going to be the same as per the design whenever there is a change in aerodynamics. So because of that, axial velocity can increase. Why it can increase? Because area is decreasing. So to make sure the mass flow rate is staying constant, so the velocity has to increase by the amount that compensate the decrease in area. So all these things can happen. So if that is the case, then our statement 2 is now correct. It reduces the flow area. The first one is correct. What about the third one? This is where it becomes a bit tricky. What about the third option? Do you need higher power?
Yes, sir. We need higher power because since the blade aerodynamics has changed, so I think
Hmm.
it's not delivering the desired pressure issue. So to compensate that, we need to supply more power and higher rotor speed.
Okay. So now to address that one, how do you calculate the pressure rise in the compressor? So usually by the stage work, right? If you have a stage work, you can write that one in terms of say Cp delta T, right? The um, that is nothing but total enthalpy change in the stage. So this one can also be written in terms of velocity triangle, right? So take an example of axial flow again, axial flow machine. So you can write this in terms of velocity triangle. So if you write that one, you get something like UCA times. So basically you are using the Euler equation that says the energy transfer in any rotating machine is nothing but rate of change of moment of momentum. That's the torque change. So that comes out like U2 CT2 minus U1 CT1. So since you are rotating at a given RPM, say, so the the blade velocity is not going to change, so u is constant, so that's nothing but ct2 minus ct1. So now ct2 from the velocity triangle, if you go back and check the axial flow velocity triangle, you can easily conclude that it can be written as ca tan alpha 2 minus ca tan alpha 1. So this is nothing but u ca tan alpha 2 minus tan alpha 1, or you can also write in terms of beta, that is fine. But my point here is this one can be easily used to compare the pressure ratio. If you use the compressor efficiency, how do you define the compressor efficiency? Work actual to work ideal, work ideal to work actual, right? So you can write something like that, the pressure ratio divided by delta T naught in the stage for stage efficiency. So now you compare this one, you can easily get it from here, from the work done, and that one you can also relate it to the velocity. So now I will just go to the next page. So the efficiency can be written in terms of T naught, or the pressure ratio can be written as delta T naught times eta C divided by T naught 1 plus 1 whole to the power of gamma by gamma minus 1. And this delta T naught I can write in terms of u Ca tan alpha 2 minus tan alpha 1 divided by Cp times eta C plus 1 gamma minus 1. Now, what is the effect of change in area that is going to affect the axial velocity, right? So if the axial velocity is going to increase, what happens to the pressure ratio?
Increase.
The pressure ratio is increasing, right? If the contamination is directly increasing the pressure ratio, why do you even have to do a perfect aerodynamic design in the first place? You can do highly irregular shape where you can increase the axial velocity, right?
Yes, sir.
Doesn't it contradicts your understanding of the compressors?
Sir, why, sir, CA like axial velocity will be affected? Uh, that is,
That's what your relations are telling you. If CA is increasing, you see like a pressure ratio is increasing. This is where like you have to understand your concepts really well. This is not like if CA is increasing, you are like you are getting the higher pressure ratio. So you have to understand this in the other perspective, that is, if like my compressor is designed to operate for some pressure ratio, and if CA is not, like, remember this CA, what you see in this equation is axial velocity that is assumed to be constant. the derivation what you do to get that work transfer in the compressor is making axial velocity as a constant parameter. That is why you could take that CT2 minus CT1. In that equation you have written it as Ca tan alpha 2 minus Ca tan alpha 1. So you could take the Ca out only by making sure that Ca is constant. So these things we have to be very careful when you compare these things, the pressure ratio versus axial velocity and all, because in our case the axial velocity is increasing because of the contamination. So we are not getting axial velocity as a constant parameter at the end of the operation. So this expression is valid whenever you are talking the incoming axial velocity is being increased. But we are getting increase in axial velocity not because we are increasing the inlet axial velocity. It is because the given axial velocity is accelerating at some sections of the compressor owing to the effective area is decreased now. That is why. So we have to be very careful here while making these decisions. So of course whatever you said, the power required is going to increase is correct. I just thought of bringing this expressions because these are the places where we can easily make mistakes by just looking at the formula and see like, yeah, this is what happening. It is guiding me that this has to increase. So these kind of judgment you cannot do whenever you look at questions which actually asks your understanding of the fundamental concepts. Okay, yeah. So if you go back and you look at the compressors, you know that like any losses which occurs in the compressor has to be compensated by giving that extra input power. So sometimes you refer it as the power input factor. So you refer it as gamma or omega UCA times tan alpha 2 minus tan alpha 1. So this is nothing but a power input factor. So in ideal scenario, this is the work done which is enough to get the given pressure rise, but since there is a loss within the compressor performance, so you are going to give that extra power from the turbine or whatever the source that is running the compressor. So you are going to give that extra power to compensate the losses so that you can still get the same pressure ratio. So you have to give that extra power. So usually this power input factor is going to be greater than 1 because that is the extra thing you are giving. So if you go back to the question, so all 1, 2 and 3 the statements are correct. Clear? So you guys have any questions from this topic?
Sir, here see in the formula this alpha 1 and alpha 2 are the flow angle, or I think flow angle.
Air angles. Yeah, flow
Okay.
angles in general, flow angles, or when it comes to gas turbines, it's air angle. So those are the angles at which the absolute velocity is entering or leaving the stage. Got it?
Yes, sir.
Yeah. Okay. Yeah, this question is coming out of a rocket propulsion. Though they mentioned they are not asking anything from rocket propulsion, but they did ask one question. The thrust of rocket engines is directly proportional to the flight speed, directly proportional to the square of the flight speed, inversely proportional to the flight speed, or independent of flight speed. What do you think?
Independent of flight speed, sir.
Okay. Anybody else?
Uh, because, sir, if we take the air breathing engine, the formula is mass flow into change in velocity. Like the exit velocity, like exhaust velocity minus the inlet velocity. So here, since rocket engine, there is no nothing is like inlet velocity here. So it will
Hmm.
be the mass flow of the exhaust into the velocity of exhaust. That will be the force or thrust. So that is will be, I think that, then this equation telling it will be independent of flight speed.
Okay. But why do you generate the thrust in the rocket engine?
Uh, like for why do we, sir, didn't get the question, sir?
Why do you need a thrust
So
from a rocket engine?
to move it forward, like to against the
Hmm.
gravity, to overcome the gravity
Hmm.
and move it
So
forward.
to move it forward means what? So rocket is moving with some forward speed.
Yes, sir. But thrust, sir, did not like depend on the flight speed, because thrust.
Hmm. Yeah. So I'm simply messing with your idea. It's fine. So whenever it comes for rocket engine, as you said, that's perfectly correct because these are not air breathing engines, right? So you have a forward speed for vehicle, but the thrust is generated due to the ejection of the mass which is uh, from the rocket nozzles. So what you get here is like, say it is ejecting mass at a rate of m dot and at a velocity of ve. Maybe there is a pressure difference, exit plane pressure and ambient pressure are different. So your thrust equation would look like m dot ve plus the pressure thrust, right? So the thrust of a rocket engine has nothing to do with the forward speed, but the forward speed is actually dependent on the thrust what you are generating. Getting? So the forward speed is actually function of your thrust, but thrust is not a function of forward speed, right? So everybody clear here, right?
Yes, sir.
Okay. What about this question? The engine pressure ratio is defined as. This is again straight out of a memory, like it's a memory based question. So I can understand why they are using this air engine pressure ratio in aircraft safety examinations and all, because if you look at the aircraft instrumentations in the aircraft cockpit, like if you see the different instrumentation, the one of the instrument you see is the engine pressure ratio indicator. So this is the direct measure of like what thrust you are actually generating from the engine, because there is no other way you can measure the thrust of an aircraft. So engine pressure ratio or the RPM indicators are two methods through which you can actually measure the thrust from an aircraft. So now, as I said, this background of what engine pressure ratio indicator and all. So can you guess what is the correct answer for this question?
Sir, my guess will be C, the ratio of turbine exit pressure to compressor inlet pressure.
Hmm. Debanjali has a different view. So why you think option A is correct? Okay. So for this one, option C is correct. So it is defined as the total pressure at the exit of the turbine to the total pressure at the entry of the compressor. So that gives you the overall total pressure ratio of the cycle. So whenever you are talking about the thrust produced by an engine, so you will be talking about the cycle through which the engine is operating. So it is basically the highest total pressure to the lowest total pressure in the Brayton cycle. So that is how you define the engine pressure ratio. Okay. In a ramjet engine, the inlet static pressure rise is achieved by option C, right? So we use diffuser to do that job. So see, the venturi meter and tailpipe has nothing to do with the ramjet operation. So they are straight away omitted. The nozzle is a duct where you accelerate the flow, not decelerate the flow. If you accelerate the flow, the pressure will expand, not rise. So this is not correct. So the only correct option will be diffuser, in which you do this ram pressure rise. I think this is going to be our last question. A turbine develops 9,000 kilowatt when running at 100 rpm. The head on the turbine is 30 meter. If the head on the turbine is reduced to 18 meter, what is the speed? Okay. So this question is not exactly from aircraft propulsion part. So it is more general to the turbo machinery, especially when you are operating the pumps, right? So this head, the pressure head, what we talk, is usually applicable to the pumps. So if they say like it is giving 30-meter as the pressure head, that means the pump is pumping the fluid above the ground level about 30 meters. That's the power of that particular pump. So if the pump is giving more head, means the pump is delivering more work. So the pump is much more powerful. That's how it works. So these terminologies are all comes for the turbo machineries in general, especially dealing with the pumps. So this is again going the direct formula based question. There is no way like you can derive everything from the scratch. So from the given information, you have to know the formula which relates this idea. Say for a pump which is delivering a constant power, say, so we have a direct relation for the pressure head to the rotational speed. So that gives us that the rotational speed square is directly proportional to the pressure head. So now if you look at this one, what you have, the pump 1 has a rotational speed of 100 rpm, and the pressure head, let me call it as ph, for the pump turbine 1 is going to be 30 meters. So now in the second scenario, the same turbine now delivering a head of 18 meter. It is reduced to 18 meters. So now they are asking what is the corresponding rotational speed. So that means N1 over N2 is going to be square root of pressure head from 1 to pressure head from 2. So now implies N2 is going to be N1 times square root of pressure head 2 to pressure head 1. So that is going to be N1 times square root of what you have, 18 over 30. So this is 6 3s are 6 5s are 3 by 5, square root of 3 by 5 times N1 is 100. So if you calculate that one, so you get 77.46 as the rotational speed. So clear?
Sir, how we have arrived at this proportionality, sir?
Yeah, that's what I'm saying. Like this proportionality thing is coming out of the turbo machinery. So this is not exactly coming from the gas turbine engines. If it is a gas turbine engines, then this relation looks very different. So in gas, like since it is asked in the propulsion part, so I am just bringing this problem here. So say like the one way to arrive this kind of relations is by doing the non-dimensional analysis. You see, you guys know the idea of this Buckingham pi theorem, right? So you list out all the important variables involved in the problem, right? X1, X2, X3, like that, and you try to reduce it to the number of important non-dimensional numbers. So say like I have 4 variables that is important to the given problem, and I can measure them using 3 fundamental dimensions, say like the mass, length and time. So now the number of variables is 4 and number of fundamental dimensions required to represent the variables is 3. So the number of non-dimensional group can be 4 minus 3, that is going to be 1. So you get one non-dimensional number if you have a case like this. Similarly, whenever you have a turbo machine or whenever you have a gas turbine engine, so in the gas turbine engine we have a 7 important variables like P01, P02, and you have a diameter of the rotating machine, you have a rotational speed of the machine, and you have a mass flow rate of the fluid, and you also have the type of gas you are using and the temperature. So we can combine them as RT01 and RT02. So now you have like 1, 2, 3, 4, 5, 6, 7 variables, and the number of fundamental dimensions required to represent these variables is going to be 3. So MLT are sufficient. So you are going to get a number of non-dimensional group, that is 7 minus 3, that is 4. So you get a 4 non-dimensional groups, say like P02 by P01, and you get this T02 by T01, and you also get non-dimensional speed that is related to n and root T0. So I am not, so there is a diameter, there is r, and there is other things. So similarly you can get the non-dimensional mass flow rate, m dot, which is non-dimensionalized with T0 or something like that. So you basically get 4 non-dimensional numbers like pressure ratio, temperature ratio, non-dimensional speed, and a non-dimensional mass flow rate. So if you remember from your gas propulsion classes, or if you remember from your propulsion textbooks, so you usually see the plots like pressure ratio versus mass flow rate, right? Non-dimensional mass flow rate as a function of non-dimensional rotational speed. So you call them like compressor maps, turbine maps and all, right? So this is one way to approach, so like how they are actually related. The other way is like you have to start from the scratch to derive the power or derive the work done or derive the uh, work transfer kind of ideas from the first principle methods, like considering the um, turbo machinery which is operating at this condition or such condition and like that. So it's basically like a derivation. So then you are going to get a relation at the end of the derivation stating like how your rotational speed is related to the power. Usually power delivered by the turbine are related with the torque times the rotational speed, right? So that gives you the power. So how torque is related? It is rate of change of momentum. So basically I can write as moment of momentum. So the momentum is mass times velocity cr2 minus cr1 times momentum, that is the moment arm, right? So that is going to be radius times the angular velocity. So angular velocity is what? That's the rotational speed. Let us keep like that only. So now if you look at CT, CR cross R or CR cross R, so that again gives you the this is going to give CR cross R, radial velocity vector cross product with the radius. That is going to give you the vector in the perpendicular direction. So that is going to be CT kind of thing, the tangential velocity, that is perpendicular to both radial vector and the radius of the machine. So if you do that, what you get is power as a function of torque. So this formula you might have used, right? 2 pi nt over 60 to calculate the power for the rotating machine, right? Where T is torque, N is rotational speed. So you can basically derive it from the first principles. So at the end you get in this way. So now you see how this rotational speed and this torque are related. And now from this question, if you want to see the relation like this, then you have to relate that, because it is already given the power which is developed. So now you have to relate the torque to the pressure head. So if you can relate this one, you should end up this relation. They are related in this way. So this is quite complicated in a way that like how you can approach, like I'm talking in terms of like how you can solve these problems in exam. So if this question comes in the exam, right, like which is asked in previous exam, so then you really don't have time to do all these steps, right? Like can you really do the derivation during the exam, that you have to recall something from the concepts and do the derivation? You can recall the concepts, but the derivation is not that easy to recall, right? There are like number of steps you have to do, number of intermediate assumptions you have to take while doing the assumption. You might do it, but it will take all your time to do all these problems. So the best option would be go ahead with the formulae, right? So if you remember the relation, how they are related, you can directly answer these questions. That's what I said. So by looking at the given questions, what I understood is like this is similar to ISRO papers. They also ask these kind of problems only, like where they ask a memory based question or the direct formula substitutions. So you have to go through this syllabus very thoroughly, and you have to follow the formulas which is involved in the subject. So then if you look at a few questions from those formulas, then you are fine with that, because you know how to solve those problems. So they are all direct substitutions. It is compared to gate, it is very straightforward. So you are getting my point, right?
Yes, sir.
Yeah. So I usually don't tell people to mug up the formula and do the problems, but since these questions demands you to remember these formulas, that is why I'm asking you to focus on those things. So you have to rely on certain formulas where you can do these direct substitutions, right? Not the stepwise substitutions. These are all direct substitutions. So like just one step or two steps. So these problems, these kind of formulas, you have to concentrate while you are even if you are mugging up, you have to concentrate, but never forget the concept behind that formula. That is very, very important whenever you are trying to answer the theoretical questions, such as like the rocket propulsion part, right? Like how the forward speed is dependent. So there you see, like the formula is not just enough. Like you have to understand whether it is non-breathing engine, air breathing, non-air breathing engine, or air breathing engine. Those kind of things you have to remember, recall. Or the contamination problem, that was a very, very interesting problem, because like there you have to recall so many things before judging any correct answers, right? So these things where like you have to focus on the concepts like gate, but while also you have to remember few formulas that gives you a direct substitution kind of thing. You have like number of places where you can get this direct substitution formulas, just like this power and torque ratio relation, or the power and this rotational speed relation, or there are so many ways, like depending on how they are asking, you can do this. Okay, yeah. So that concludes our discussion on the questions which is being asked in propulsion part. So what I suggest you guys to do is, by looking at the questions, what I think is like you guys have to read one textbook from core turbo machinery, that is designed for mechanical uh, courses, not for aerospace courses, but from the mechanical engineering side. So there are books on turbo machinery like steam engines, steam turbines, and all, right? So you have to go through one textbook at least which deals with the turbo machinery. So it looks like whatever questions we saw, right? So at least one or two questions, they are actually coming out of the uh, turbo machineries, not from the gas turbines. So yeah, so you have to go through at least one textbook. And there is one more textbook called this aircraft safety manual or something, that is available in the IGC website or IGC Google Drive, that is aviation maintenance technician certificates. So that book, the module on propulsion, you can actually go through. Don't just rely on that book. So you have to also you are already familiar with this textbooks like Cohen and Rogers, or like the Rolls-Royce jet engine textbook. So they are all very good textbooks to refer. And also you can go through this maintenance manual kind of book, where you can actually kind of sense like what they are actually interested in, what kind of topics they are interested in, this aircraft safety um, courses. So that is also good reference points to pick out the topics you have to study, right? Okay then. So do you guys have any questions? Okay, then if there are no questions, then we can stop the session here. Okay. Yeah. Once again, thank you for your attention.